Hey guys, I'm a verified educator at Unacademy, and along with that, I'm also teaching live at Unacademy Plus. To access my live classes, you can take Unacademy Plus subscription. Now, Unacademy Plus offers some interesting features apart from live classes, which include detailed and complete explanation of a particular course. Then there you have problem discussion for self-evaluation. You can also watch recorded version of the class in case if you miss out any live session. You have regular doubt clearing sessions for doubt clearing and to clarify all your problems. You also get access to the WhatsApp group to clear and discuss problem among the other plus students. Now, if you have found these features interesting and want to join Unacademy Plus, I'll recommend you to use my referral code, that is N_Huda, to get 10% discount on the subscription fee. Now that's all about Unacademy Plus. Let's continue with our video. Alright, so hello everyone and welcome to the channel. So this video is going to be about the kinetics of reversible reaction. Now in this video I'm going to cover like all the basic aspect of this of a particular reversible reaction. Also I'm going to derive the equation that how you can determine the rate constant for the forward reaction and for the backward reaction. Also like at the equilibrium what will happen and what equation you will get. So those things I'm going to cover in this particular video. Now this is going to be important topic because like direct question has not been asked from this topic yet, but as consecutive reaction, as parallel reactions are important, in the same way reversible reaction is also one of the important topic from your chemical kinetics, and it is least touched topic. Okay, like people generally ignore these kind of reactions, but yeah, after watching this video I hope that this topic will be cleared for you and you'll be able to solve question related to that. Yeah, one more thing that this was actually asked by you guys to make, like I was asked to make this video by many of you, so that's why I'm making, and soon I'll try to cover that consecutive reaction as well, and after that video I'll try to make a video on the quotient part, like whatever questions will be asked based upon this particular topic, right? So this this is going to be like that. Okay, so in this video there will be no question. I am not going to discuss any question from the previous years of CSIR net or gate. I'm just going to tell you that how this equation comes and all. Okay, so first of all let's talk about reversible reaction. In the reversible reaction you have reactant and you have a product, and like both of them are getting simultaneously formed, so that means reactant molecule is getting converted into product molecule and your product molecule will be getting converted into reactant molecule simultaneously at the same time. Simultaneously means at the same time. Now here this is forward reaction, the rate constant for that is Kf. This is the backward reaction and the rate constant for that is Kb. Now if I denote it as A and B, so I can write it like A is getting converted into B by rate constant Kf and B is getting converted back into A by rate constant Kb. Now in kinetics, that means in chemical kinetics, reversible reactions are the reaction in which conversion of reactant to product and vice versa, means from product to reactant occurs simultaneously. So these kind of reactions are called as reversible reactions. Now let's try to see mathematically that how we'll do these kind of questions. Okay, so let's take a condition, or let's take a case in which we have molecule A which is being converted into B, and yeah, so let's say initially when the time was 0, initially you have a small a as the concentration of A molecule and small b as the concentration of B molecule. Okay, so these are the concentrations of your A and B at some time, at some initial time t. Now if you have like if you take at some certain time t, at some time t, so what will happen, that some part of A will be dissociated or it will be converted into B. So let's say small x is the part of A, that means reactant, that is being converted into product. So the concentration of A will be reduced by x amount and the concentration of B will be increased by x amount, right? Because A is getting converted into B. So this will become A minus x and this will become B plus x. This is very crucial and very important to know. Okay, why? Because x is the it's the amount of molecule of reactant which is getting converted into product. So from A your x amount is being taken out and in B that amount is getting formed. So that is done. Now at equilibrium time, when the time reaches when the reaction reaches equilibrium, at that time, let's say the concentration of X now is taken as XEQ, because that will be specified concentration of A, which is getting converted into B. So that's why we have specified it as XEQ. So XEQ is the concentration of reactant molecule which is being converted into product. So XEQ is nothing but the concentration of the reactant molecule which is being converted into product at the time of equilibrium. Now degree of dissociation, that means that is denoted by alpha, at any time t is given by X by A. So the part that is being converted into product divided by the initial concentration, and at equilibrium it will be like XEQ by A. So that's how you define degree of dissociation, and these will be the formula for that. Now let's come into the real part. So the rate of A, that means RA, will be given by Kf into A, that means rate constant of formation of A into concentration of A. So concentration of A was A minus X at any time t, so that means rate of A will be given by like rate of formation of A will be given by Kf A minus X. Similarly, rate of formation of B will be given by Kb into B, that means concentration of B, that is B plus X at any time t. So that's why it will be like Kb and B plus X, right? Now the rate of the reaction will be equal to, actually the net rate of reaction will be equal to rate of forward reaction minus rate of backward reaction. So you can put both the values from here. This is the rate of forward reaction, this is the rate of backward reaction. You can put the values. Rate of reaction is negative of concentration of reactant divided by time. So I have just put the values. The concentration of A is A minus X, or you can express this in the terms of the concentration of product, or you can like the concentration of molecule which is getting formed. So instead of writing A minus X, I can write it like, instead of writing minus dA minus X, I can write like plus dx by dt, and the right hand side is same as it is. So this is our equation number 1. Let's put it as equation number 1. Now that was at certain time t. Now what will happen at equilibrium, that will be little specified. Okay, so at equilibrium your rate of forward reaction will be actually equal to rate of backward reaction. Now the rate of forward reaction is Kf into AEQ, that is concentration of A at equilibrium, and similarly rate of backward reaction will be Kb into BEQ, that means concentration of B at equilibrium. Now if I divide it, so it will become Kf by Kb, that is actually equal to Kc, that is the rate constant at equilibrium, or the equilibrium constant, and on the right hand side I'll be having BEQ by AEQ. I have just cross multiplied. Okay, so Kf by Kb is equals to BEQ by AEQ. Fine. So Kf by Kb, now I have just put the value of BEQ, that was B plus XEQ, and AEQ was A minus XEQ. So I have just put the values, and this is what I will get as the value of equilibrium constant in the terms of concentration, initial concentration of A and B, and the concentration of A which is getting converted into the product during that equilibrium. Now again I can take both the things equal. Again, whatever we have done in the previous step, same thing we can do. I can just take both of them, both of these things equal, and now I'm going to divide both side by Kb. I'll get Kf by Kb, Kf by Kb, and on the right hand side I'll get B plus XEQ. I'll take XEQ on the on the left hand side to get the value of B. So I got value of B, let it be equation number 3. Okay, now this particular equation number 3, I'm going to put it in equation number 1. Now remember equation number 1, that equation was actually this equation where we were having B over here, right? So dx by dt is equals to Kf A minus X minus Kb into B plus X. So this was the equation. I am going to put the value of B over here. Why I am doing so? Because I want to have a relation between dx, dt, and I need only equilibrium values over here. So that will help me to integrate later on and to get the to get the required things. Okay, so once I substitute the value of B from equation 3 to equation 1, I'll be getting this, that is dx by dt is equals to Kf A minus X minus Kb, and that's where I was having B. So I've put the value of B, that is Kf by Kb A minus XEQ and plus X, because that was B plus X. Okay, so in the place of B I have put the value of B from just this equation. Okay, so whole this thing I have put over here, that's all. Now just the mathematics and the calculation and just the equation, like just solving the equation. So multiply inside, this kb and this kb will be cancelled out. I'll just get kf a minus xeq over here. This kb will be multiplied by xeq over here, so it will become minus 1 is plus kb into xeq, and this kb will again be multiplied by x because this whole bunch of thing is in the bracket. So I'll be getting plus minus will be minus kb into x. So that's what I am going to get. Now from here I can take kf constant or kf as a common over here. I'll get a minus x minus a plus xeq. So that a and this a will be cancelled out. I'll just get xeq minus x. So xeq minus x, that's what I'll get. Plus over here I can take kb constant, so I'll get xeq minus x. So basically in both these values I just got xeq minus x as constant. I have taken that as constant. I got kf plus kb. Okay, so dx by dt is equals to xeq minus x into kf by kf plus kb. Now I can just integrate this because I want to get the final answer. So on integrating, what I will get, the dx divided by xeq minus x, and on the right hand side I'll get kf plus kb because these are constant, so these won't get integrated. I have to just integrate this dt part that I have just multiplied on the left side. So you can do two things. Either you can take the infinite different integral and then put the value of constant and all, but that will just include 2 or 3 steps more. So I have just taken definite integral. So concentrations from 0 to x, because x can have just the value, minimum value 0 and maximum value x. Time can be either 0 to t. So on integrating, I'll get ln, that is natural log of xeq divided by xeq minus x. On the right hand side I'll get kf by kf plus kb, and this dt will be integrated to give you t. Now the final answer which you will get will be, this, that is kf plus kb is equals to 2.303. I have just converted that natural log into log base 10, so that will be 2.303 upon t log xeq by xeq minus x. Now if you recall this is nothing but actually equal to this equation, that is k is equals to 2.303 upon t log a upon a minus x, right? So this was the equation for a reaction, like for the first order reaction, right, where a was the initial concentration. Now instead of initial concentration you have the concentration at equilibrium. Okay, the concentration of the the concentration at the equilibrium, and x is the amount of a which is getting converted into b. So, or you can say the part of a which is being converted into b. So this is nothing but representing that this kf plus kb is first order, like it will follow the first order kinetics. So if I plot a graph for the for concentration versus time, so I will see that the concentration of A will be decreasing and the concentration of B will be increasing at a particular time, and on reaching equilibrium these concentration will become parallel to each other. Okay, so these concentrations will become parallel after reaching the equilibrium. So that is to be noted. Okay, if it is not a equilibrium reaction, then obviously these concentration will keep on decreasing and this will keep on increasing, but on reaching equilibrium they will become parallel, and now the increase or the concentration will become constant after reaching the equilibrium. So that's what something to be noted over here. Okay, so this is one part of this particular reaction, and this is done. Okay, so what you got is this like the reaction, equilibrium reaction actually follows first order kinetics, and this is the value, this is the equation which you get. Now using this equation you can calculate mathematically all the different values. Let's try to go a little further and try to find out the value of kf now. Now in order to find out the value of kf, we have taken again the equation number 2 which we have written earlier. So in equation number 2 we were having kf by kb is equals to b plus xeq by a minus xeq. I can find out the value of kb. I have just multiplied, cross multiply, and I'll get kb is equals to kf and a minus xeq by b plus xeq. Now I can just add both side kf. Okay, I'm adding kf both side just to form it as kf plus kb, so that I can substitute its value in this equation, kf plus kb. Okay, so just to put it over here I am doing so. So I am adding kf both side. On the right hand side, when I will add kf, I can take that common, and that will be like kf, and in the bracket it will be 1 plus a minus xeq by b plus xeq. On solving the denominator, like on taking the denominator, I'll be having b plus xeq plus a minus xeq. this term and this term will be cancelled out. I will just get a plus b in the numerator. So a plus b by b plus xeq, and kf is over here. This is equation number 5. This is nothing but kf plus kb. Now I can just substitute its value in our this equation which we have calculated. Okay, so I'm going to put this value in the place of kf plus kb. So I'll get kf a plus b divided by b plus xeq, and on the right hand side I was having 2.303 upon t log xeq divided by xeq minus x. Now just multiply this thing on the other side, and that's what you got equation for kf. So the rate constant for the forward reaction you can calculate with this equation, that is kf is equal to 2.303 upon t b plus xeq divided by a plus b log xeq divided by xeq minus x. So this is the equation which we wanted to find out at the end. So this is the end of this derivation, guys, and this is how it has to be done. I hope this is like you got to understand that what are the things we are doing actually, and if you have doubt, like it will be advised to you guys that like while watching this video, make a note of it. Okay, that will be like then you can read out in a much better way, and you will not forget this thing. Okay, so that was about it. Let's take one more case and end this video over here itself. Now this is a case which I am taking is a case in which we have a first order opposed by the second order. That means if the reactant is only first order following the first order kinetics, and the product side is the second order kinetics, means you have two products out of A, and it is in equilibrium, like Kf and Kb are over here. So it's an equilibrium reaction, but on the reactant side you just have one molecule, on the product side you have two different molecules which are being formed. So the simpler basic things are written over here. Now, right, so the differential equation for this thing you can write down using the steady state approximation and all. So your dx by dt, basically the rate law equation, you can write down easily, right? No need for steady state approximation, sorry, don't need a steady state approximation over here. So yeah, dx by dt will be equal to kf and a minus x minus kb into x square, and on integrating the integral equation, I have just written the equation. I'm not going to do all bunch of things because this is going to be a lot of calculus and lot of solution over here. So this equation, just write it down somewhere, it will be very useful to you guys. So kf into t into 2a minus xeq by xeq is equals to 2.303 log, this whole thing is in log, that is log a into xeq plus x bracket a minus xeq divided by a xeq minus x. So this is the equation when you have binary product getting formed from a single like reactant. So that's all, guys, that's all for this video, and I hope you guys like this, and if you have any doubt you can ask me in the comment section below, and that's all from my side. Thank you so much for watching. Have a great day. Bye bye.